to Corona Chemistry, to what may be the last video for quite some time. We're going to be discussing the concepts of solutions solubility and the calculations associated with molarity, along with acids and bases and pH calculations, which goes in conjunction with those acids and bases. As always, if you're watching this video on YouTube, feel free to utilize the links that go to the notes and the slides that we're using in front of you today so that you can follow along and do the example problems. So off we go! Solutions and solubility is what we're kicking it off with. So first of all, what is a solution? Well, a solution is just another term for a homogeneous mixture, which is almost always typically something dissolved in water. And remember what a homogeneous mixture is. It means that if you look at the left, if you look at the right, if you look at the top, if you look at the bottom, they all look the same. Everything is evenly dispersed. And so one of the most common examples for that would be salt dissolved in water. Well, if you've got salt dissolved in water, that's two components. You have your solute, which is the salt that is being dissolved, and your solvent. Almost always you have more solvent than solute. Water is the universal solvent. Why do they say that? Well, it's because water has, as we discussed in prior videos, water is very polar. And because it's very polar, it's very, very good at dissolving other polar compounds. And there happen to be a whole lot of polar compounds. It's also very good at dissolving ionic compounds because those ionic compounds will actually dissociate into their different ionic pieces, as you may have learned in previous concepts in chemistry. So anyways, solutions cannot be filtered, and that's because when you actually dissolve these solute particles, they become so small that they're just going to travel with the solvent wherever it goes. You can increase the rate in which something dissolves by doing the following three steps. You can increase its surface area. This is why if you crunch up your sugar cubes, it's going to dissolve a whole lot faster as opposed to just dropping in that sugar cube straight into your tea or coffee, whatever you're dissolving it into. Stirring it or agitating the solution is going to increase the speed in which it dissolves because what you are doing is you are disrupting the pile of solute that you've got in your solution there. And what it's doing is it's exposing more solute to the solvent, right? If you just have it in this big clump, there's no guarantee that your solvent is actually getting to every single molecule, every single atom of whatever you're trying to dissolve. So stirring is going to speed that along. And number three, you're heating up a solution. Heating up a solution typically increases the solubility. Not all examples, there's exceptions to everything, but typically it does. I would say 98, 99% of cases. However, when I heat up a gas, it decreases its solubility. Why? Now, I don't know why you would ever do this, but if you ever left an open cup of Coca-Cola on the front porch, right, in the middle of the hot Texas sun, or you left a cup of Coca-Cola inside of your refrigerator, which is going to lose its carbonation quicker? Well, it's going to be the one that you left on the front porch. Now, both are disgusting examples. You should always seal it, right? Are you kidding me? There's a way to consume Coca-Cola, but the reason why is because if you are going to heat something up, it's imbuing those carbon dioxide molecules with more kinetic energy. Therefore, they have the energy to branch out and escape the confines of its container, therefore leaving your Coca-Cola a disgusting and flat mess. So don't be that guy. Don't be that guy. You can have solutions of any combination of the states of matter that you've discussed prior in chemistry. So here are just a few examples. Of course, there's hundreds, thousands beyond this. But you can have a solution is not always just a sprinkle solid in water. It's not always that. But here we are. The next term that we are going to discuss are electrolytes, which if you're an athlete or you're involved in any extracurricular activity that causes you to sweat, well then almost surely you've heard your teacher or your coach yell at you about replenishing your electrolytes. As you sweat, you're losing electrolytes, which are very, very vital minerals and very vital substances in your body to keep its homeostasis. Well, an electrolyte, as you might be able to conclude from the name, has a little something to do with electricity. And electrolytes, when they are dissolved in water, enable the water to conduct electricity. You see, water on its own doesn't actually conduct electricity. Distilled water is water that has been, boiled through several times in order to make sure that there are no outstanding ions within the water. And so if you were to take a bath with distilled water and let's say accidentally drop a toaster into it, not saying that you're purposefully trying to do it, let's say you're accidentally dropping a toaster into your bathwater, if it were distilled water, you'd actually be totally fine because there's no ions in there to conduct electricity. However, let's say you're swimming out in the middle of the ocean and there's a lightning storm above, well, there's a whole lot of salt dissolved in the ocean. I don't know if you knew that. But salt is an electrolyte. When salt, NaCl, is dissolved in water, it separates into Na plus and Cl minus. And because it creates these ions, the positives and the negatives, that's what enables the current of electricity to flow through the waters. And so if you're swimming underneath a lightning storm in the middle of the ocean, that's muy dangerous, very dangerous. And so dropping a toaster in distilled water, harmless. Dropping a toaster in salty water, quite harmful. Okay? Please do not try this at home. Please do not try this at home. But there are such things as strong electrolytes versus weak electrolytes. There are also substances known as non-electrolytes. If you do not dissociate and break up into different pieces, such as sugar, for example, or any other covalent compound, covalent nonpolar compounds, well, those are all non-electrolytes. However, the compounds that form strong electrolytes are ionic compounds, such as salt, NaCl, along with very, very, very highly polar compounds that almost behave like ionic compounds, such as strong acids or strong bases. And as we get further into this video, we're going to discuss what it means to be a strong acid or a strong base versus a weak acid or a weak base. It's not to say that the weak acid or weak base can't melt your face off. It absolutely can, but it means something slightly different. But we'll say that for a little bit later. Next, we're going to discuss a couple of different terms. They're not exactly solutions. The more so, they are heterogeneous mixtures. And those two terms are suspensions versus colloids. And a suspension, it's very, very, it's always apparent that you can see different layers. A suspension, there are different layers. And so let's read the exact definition. A heterogeneous mixture in which the solute particles are so large that it settles out unless stirred. AKA, if you leave it alone for a little bit, you're going to see a change in its appearance. Surely, this is a beaker filled with sand and water. If you were to stir it all up, yeah, the sand could be spinning round and round and round. It looks like there's some on the top and in the middle and on the bottom. But if you let it sit there, the sand is obviously more dense than the water and therefore settles to the bottom, forming two distinct layers. In oil and vinegar, right, if you've got Italian salad dressing, right, maybe you've seen your waiter shake it up before he pours it onto your salad by your table. But if you leave it alone, the vinegar is going to go to the bottom and the oil is going to sit on the top. It's just differences in density, but those are examples of suspensions. But they are certainly not homogeneous mixtures as our solutions were. And a colloid is a heterogeneous mixture. However, you can't always tell with the naked eye. So a heterogeneous mixture are particles that are larger than a solution but smaller than a suspension. AKA, you can leave them alone, and they will never settle to form another layer. They will always float within the liquid. Now, a couple of examples of this are milk and blood. That doesn't mean combining the two. That's disgusting. That means two separate examples. Milk is a colloid and blood is a colloid. Imagine what's in blood, right? You got the white blood cells, you got the red blood cells, you got the platelets, you got all the other jazz in there, right? And there's no guarantee that they are evenly mixed, which is why it's not a homogeneous mixture. It's a heterogeneous mixture. But the telltale sign of how to differentiate a colloid from something else is what is called the Tyndall effect. If you shine a light through it, if you can see the pathway of light, that means the light is being scattered. AKA, what is occurring is these particles are so large that they are inhibiting the pathway of light. Therefore, they are scattering the light. However, in the example of a true solution, such as salt and water, when salt is dissolved in water, the particles of salt are so small that they don't inhibit the pathway of light. Therefore, you get what you see on the left-hand picture. Let's just imagine this is salt dissolved in water. I can't see the beam of light, right? Why can I see it here? Well, it's because whatever this is, it looks like they've put a little bit of milk in a glass of water, whatever it is, right? And you can see the pathway of light because the milk particles are so much larger than the salt particles. But over here, because the particles are so tiny, we can't see their pathway. They're not actually inhibiting the pathway of light. Next, a couple more terms. Solubility is actually how much solute you can dissolve at a given temperature. Different substances can dissolve different amounts or can be dissolved in different amounts. But very typically, it's in 100 grams of solvent is how they like to regulate those. So when you're comparing values of two different substances, you can actually get a good, clear picture of what you're dealing with. And it's almost always water that it's being dissolved in. Anyways, if I've got a certain amount of stuff dissolved in 100 grams of water, I need to know what kind of solution I'm dealing with, the saturated, unsaturated, or supersaturated. Well, everything has a limit. So let's stick with the figure that they have up here. Let's say we always have 100 grams of water. If I've got 100 grams of water in a beaker or a glass, there's a limit to how much stuff I can dissolve in it. And it certainly depends on what that stuff is that I am dissolving. Salt dissolves very easily. Other compounds do not dissolve as easily. But either way, a lot of people, very, very smart people in history, have actually mathematically calculated what the limit is per certain amounts of water that they can dissolve in these various substances. Well, if you are at that limit, let's say that in 100 grams of water I can dissolve 50 grams of stuff. Well, if I have dissolved exactly 50 grams in it, that is a saturated solution. I am at the limit. Well, if I have put 51 grams of stuff in this water when it's only supposed to be able to dissolve 50 grams, well, then that is a super saturated solution if I go over the limit. But if you say under the limit, let's say I'm between 0 and 49 grams, that's certainly under 50, then that would be an unsaturated solution. There are cool examples in the real world which utilize all of these terms. Supersaturated, the most common example that I can think of is rock candy. What they do is they dissolve sugar in water. And so what they do is they heat up the water really, really, really hot so they can dissolve more sugar than they actually would normally be able to. And then they cool the water back down so there the sugar will crystallize on whatever stick or rod that you put in there, crystallizing into sugary, beautiful rock candy on your vehicle, which typically is that wooden rod that you see in the candy stores. But that's an example of a supersaturated solution. So what kind of places and venues are we going to see this? You might see it in little graphs like this. This is what is known as a solubility curve chart. Kind of looks like a spider web to me, right? All these crisscrossing spiders interconnecting the lines of their web in here. But each line represents a different substance, right? And you can see we've got various substances here. We've got covalent compounds, SO2. We've got salts, ionic compounds throughout. We've got even an acid right here, HCl. And they all have different behaviors. On the x-axis, we have the temperature, right, in degrees Celsius. And on the y-axis, it's how many grams of whatever stuff you're talking about in 100 grams of water. So in all of these scenarios, we are always in 100 grams of water. But notice that as the temperature goes up, it almost always, the line for that substance trends upward, which proves what we were talking about earlier. As you increase the temperature, you can typically dissolve more stuff in it. That's the general idea. However, you've seen a few examples. That's not the case. HCl goes downward. NH3 goes down there. SO2, which is typically a gas, or almost, it's always a gas. We said earlier that gases do not increase their solubility as you increase the temperature. They actually decrease. So this also proves what we were talking about earlier. But either way, this line represents a saturated solution. So let's look at NaNO3 right here. Let's say at about 20 degrees Celsius, it can dissolve about 87 grams or so. If you're following my cursor here, it looks like it's a little past 85, but certainly below 90. So I'm going to say 87, right? If I dissolved 87 grams of NaNO3 at 20 degrees Celsius, that's a saturated solution. If I dissolved anything less, well, that's an unsaturated solution. But if I put in 120 grams, look at how I'm obviously above the line. That is a super saturated solution. And so really utilizing these terms, it's just interpreting a graph. There's not too much to it. But there's several different types of ways they could ask you this kind of question. For example, if you doubled the amount of water, let's say they ask the question, how much could you dissolve in 200 grams of water? It's a perfectly linear relationship. If this can dissolve, 87 grams in 100 grams of water at this temperature, well, if we double the amount of water, then we can double how much we can actually dissolve in there. And so it's almost what you would expect, right? But the point is, if the point falls on the line, it's saturated. If it's below the line, it's unsaturated. And if it's above the line, it is super saturated. Just a couple more terms before we get into the main topic of solution calculations, which the big money term of the day is molarity. But here we go. General rule of thumb, and this is something that you typically face as you go into AP chemistry or college chemistry when you're dealing with scenarios in the lab. This is not so much a general chemistry question when you're in your typically sophomore or junior year of high school. But the general rule of thumb is if I need to dissolve something, I need something that is chemically similar to it. And so the term that they use is like dissolves like, meaning that if I need to dissolve something that is polar, I would use a polar solvent, which is why water is so good for that, right? If I've got something that's polar, water is going to be able to dissolve it because water is polar. But if I've got something that's non-polar, like oil, well, then water's not the best call, because water is polar and oil is nonpolar. Therefore, they don't get together, which you've seen in multiple images throughout your life, including this one in the bottom right. Look, they don't go together. And another term for not going together is immiscible. Immiscible. Miscible means, it kind of sounds like mixable. Miscible or mixable. They dissolve within one each other, but oil and water, they absolutely do not. They form different layers. So if I wanted to dissolve oil, I would need something that is nonpolar, perhaps a compound like hexane, something like that, if you're familiar with that. So before we get into our calculations, let's go and talk about concentration, molarity. Concentration is a big fancy word, or a calculation or a measurement for how much stuff you've got dissolved in a certain amount of liquid. And that liquid is almost always water in all of the circumstances that we are talking about today. But look at this image, right? More stuff, more concentrated. Less stuff, more diluted, less concentrated. If you've ever gotten those cans of frozen orange juice from the grocery store, you're definitely not cracking those open and taking swigs from that. Why? Because that is juice concentrate. You're supposed to water it down. I believe 1 can of that is supposed to go in like 2 jugs of water. You're supposed to spread it out. You certainly should not be drinking straight from the can. If you do, you're a freak of nature. Okay, I'm not afraid to say that. You're a freak of nature if you're drinking from the juice concentrate can, right? I imagine you take 1 lick of it and you're just puckering your lips like crazy. First they're sour, then they're sweet, then they're gone. It's just straight sour. This is not a Sour Patch Kids conundrum. You're just weird, okay? So more stuff, more orange juice concentrate, more concentrated the solution, aka the more flavor we would experience if we're equating this to beverages, something like that. But molarity, very, very, very important to get these units straight. Molarity is the moles of solute, whatever you're dissolving, over liters of solvent, which is almost always water here. And so what we're going to do is we're going to go into a few mathematical calculations here in just a moment. So be sure to have your calculator ready. But it is always moles of what you are dissolving over liters. So let's look at our first couple of examples. Example 1, suppose you have 4.6 moles of NaCl and 8.5 liters of water. This already has its units straight and set up for us. We have moles, we have liters. So this one's just going to be simple division. Just make sure to track your significant figures, but we'll show that on the board here in just a moment. But let's look at example 2 and 3 already. Suppose you have 13.5 moles of potassium fluoride in 1,250 milliliters of water. The issue with this question is it's not in liters. So we'd have to do a little bit of precursory housekeeping before we actually plugged it in. If we're not in liters, we're not going to get the right answer. And example 3, suppose you have 29 grams of NaCl and 820 milliliters of water. Well, now we got a double problem. I don't have moles, nor do I have liters, so I have to do 2 conversions before I actually go and plug it in. But we will solve those now. Here we are doing our molarity calculations, where we're going to start with example number 1. Suppose you have 4.6 moles of NaCl and 8.5 liters of water. The most important thing to remember and realize about the molarity formula is that it must be in moles and it must be in liters. And the great news about example number 1 is that we already have that. The only thing that we're going to watch for is rounding to the proper number of sig figs after we plug and chug it in. But we've got our 4.6 moles over our 8.5 liters. Each of those measured values have 2 significant figures, so we're just going to make sure that we round that to 2 sig figs. 4.6 divided by 8.5. And we get 0.54, and there's 2 different ways you can write this, really. You can just make your unit a big M for molarity or concentration, or you can actually, if you're looking at other places online, you'll see them write the concentration of certain solutions in brackets like so. Whatever your teacher's looking for, though. Example 2, suppose you have 13.5 moles of KF in 1,250 milliliters of water. The only issue with this is that the volume that they provide for us is not in liters, and it must be in liters according to this formula. So the only thing we have to do is we have to convert our milliliters to liters. We already have the moles. And so, very quickly, if I've got 1,250 milliliters, all I have to do is divide that by 1,000, and I'm going to get 1.25 liters, like so. Then I'm going to take my moles, my 13.5, and I'm going to divide by that 1.25. We have 3 sig figs in each of our measured values, so we're going to round to 3 sig figs when it's all said and done. And we get a concentration of 10.8. Last example for molarity calculation says, suppose you have 29 grams of NaCl in 820 milliliters of water. Well, we don't have moles, nor do we have liters, so we have to do two different conversions before we plug this in. So first, let's go ahead and convert our milliliters of water to liters by just dividing by 1,000. So 820 divided by 1,000 is going to be 0.82 liters, like so. And then the way to convert our grams of NaCl to moles of NaCl is to divide by its molar mass. So you look to the periodic table, look for Na, look for Cl, and add them together, and that's the molar mass. Sodium has a molar mass of 22.99. Chlorine has a molar mass of 35.45. So when it's all said and done, that has a total mass of 58.44 grams per mole. So now I'm going to take the 29 grams that they provided, and I'm going to divide it by that value, 58.44, and that's going to give us our moles. Now, if you can, try to avoid rounding here and use that second answer function in your calculator. So I'm going to give it a few extra decimal places here. This is not rounding to sig figs. So 0.49624 moles is what we're working with here. And now we have our moles and our liters, so now we're good to go. Good. Put the moles on top. Divided by our 0.82. And each of our measured values that they provided for us in the beginning have 2 sig figs, so we're going to round this answer to 2 sig figs. And so that is going to be 0.61 molar. The second type of calculation regarding solutions that you're going to need to know how to do is dilutions. And so what this essentially is going to be, or the scenario that you're going to be confronted with in the real world is, let's say you're preparing a chemical for a lab, right? Let's say you're a lab aide, or maybe you're a chemistry teacher one day, and you're preparing some kind of chemical that your students need to utilize in the lab. Well, what the company does when they send you this chemical is they send you a very strong version of it. And so you don't want to use the strongest version. Well, you don't have to. You want to spread that out over the semester, classes. You need lots of uses for it. And so what you're going to do is dilute it. A more realistic scenario, let's say you're not going to go the chemistry teacher route or the lab tech route. Let's say you're going to the Chick-fil-A and you order yourself a nice large sweet tea. But little Jimmy in the drive-thru window, this is his first day on the job. He doesn't quite have the formula down, and he puts a little too much sweetener in it. Oh my golly, it's undrinkable. Oh my gosh. Well, to you, with your vast amount of chemical knowledge, this is actually a gift. Because what he has just given you is more bang for your buck. Because a foolish person, someone who has not acquired this knowledge in chemistry, would simply throw it out. They would dump it out on the side of the curb. But you, a smart chemical person, are going to participate in a dilution. You're going to water it down. Because the reason why you think that this essentially simple syrup of tea is undrinkable is because you're getting too many sugar molecules in every sip that you take. Well, what you need to do is you need to spread it out. You need to increase the distance between these sugar molecules. And the way that you are going to do that is you're going to water it down. Well, what you are doing is you're utilizing this chemical formula in front of you. M1V1 is equal to M2V2. The molarity, the concentration of solution 1 times the volume of the first solution that you're looking at is going to equal M2V2, the concentration of the second solution times the volume of the second solution. But as I said before, where you're typically going to see this in the chemical world is when you're taking what are called stock solutions, aka the very, very concentrated versions of chemicals that you receive from the companies, and you're watering them down so that you can spread them out and use them over long periods of time. So let's look at a couple examples here. What volume in milliliters of a 2.00 molar calcium chloride stock solution would you use to make 500 milliliters of a 0.3 molar calcium chloride solution? So this 2.00 is what the chemical company sent us. But we know that we don't need that concentrated solution to achieve the effect that we are going for. So why utilize something that's, way stronger than we actually need? Let's spread it out. And so this is going to be V2 and M2. We have M1, we're looking for V2. And so what you're looking for is how many milliliters of the original stock solution do I need? And then what you have to realize is that whatever you're making is 500 milliliters of that. So you're going to have a certain amount of milliliters from your original solution, and then all you're going to do is you're going to add water to it until you get to 500 milliliters. And so it's essentially a recipe on how to build the solution that you're going for. Example 5, same sort of story. If you dilute 20.0 milliliters of a 3.5 molar solution, so this is M1, the 3.5, and the 20.0 milliliters is V1, to make 100 milliliters solution. So essentially what you did is you simply put it under the faucet and added 80 milliliters of water. What is the new concentration? Well, you have now spread out the molecules, so your concentration should definitely go down. You just have to calculate it. But quite simple. Let's look to the board now. So a couple of examples with dilutions. Remember, our formula that we're going to use today is M1V1 is equal to M2V2. And that's not M for moles, that's big M for molarity, otherwise known as concentration. And so our first question that we're going to look at is what volume in milliliters of a 2.00 molar calcium chloride stock solution would you use to make a 500 milliliter 0.300 molar calcium chloride solution? What I would do is I would tackle this the same way that we did our gas laws if you watched our previous set of videos. I would label what we're working with here. M1, the original molarity, is 2.00, and they want to know the volume from that original solution that we need in order to make what we're going for here. So we're looking for V1. Then M2 and V2, we're making a 0.300 molar, and we want it to be 500 milliliters. Notice that it doesn't actually matter if our volume's in milliliters this go around. Just know that whenever we get our answer at the end, that volume will also be in milliliters. So now we are good to go and plug it in. And so now the only way that you could really mess this up in the beginning is if you put the wrong variables in the wrong spots. For example, if I put the 500 milliliter next to the 2, for example, that's one way you could mess it up. But either way, let's rearrange and let's solve for V1. Here's our original formula. And we're going to solve for V1 by dividing by M1 on both sides to get V1 by itself. Like so. And now we're going to go ahead and plug it in. And our 500 milliliters does only have 1 sig fig, so technically we are going to round our answer to 1 sig fig here. So 500 times our 0.300 divided by 2. Our unrounded answer that we get is 75 milliliters, but we're going to round that to 1 sig fig using the perfect 5 rule. That should be 80 milliliters as our final answer. Our next example for dilutions is if you dilute 20.0 milliliters of a 3.5 molar solution to make a 100 milliliter solution, what is the new molarity of this solution? So essentially what it is, I just put it under the faucet, added 80 milliliters of water to this, and we want to see how it's changed. So our original concentration was 3.5, and we had 20.0 milliliters, like so. And our new volume is 100 milliliters. And we want to find out what M2 is. So all we got to do is rearrange our equation to solve for M2. M1V1 is equal to M2V2. Divide both sides by V2 in order to get M2 on its own. And plug it in. And we're going to round this to 1 sig fig, and we get a new concentration of 0.7.
Quarantine log, day 97. After conducting a thorough investigation, I know who's behind all of this mess. It's been right under our noses the entire time. It's hip-hop sensation and rap artist Future. I mean, just think about it. Listen to the words in his song. Mask on. That's all I can show you due to copyright limitations and the prolific use of profanity. I'm going to keep following this, and I'll let you know where it takes me.
Now that we're done with our discussions on solutions, let's go into the concepts of acids and bases, along with the mathematical calculations that we can do with them as well. So kicking it off with acids, a few things about them. They're very prevalent in our diet, so you'll know that they taste sour. You know, all your fruits have, some version of citric acid, and there's some acid in there. Lemons, of course, the most sour out of the fruits. And maybe there's an example that I don't know of that you know of, you fruit connoisseurs at home, so feel free to correct me. But there's a reason why this baby is puckering his lips, right? More obscure knowledge that you might not have seen unless you've done an experiment in class. They turn litmus paper red, and they have a pH that is less than 7. So pH, very, very important in this discussion in the second half of this video. pH is on a scale between 0 and 14. Okay? 7 is that midway point. 7 is neutral, and if we are below 7, we are acidic, and if we are above 7, we are basic. And there's also different indicators in chemistry. One of the most common ones is known as phenolphthalein. And acids, phenolphthalein remains colorless while it sits in an acid. However, it has a very different indicating color when present in a base. And before we go on to anything else, let's first discuss how to name acids, which this might be a review for a lot of you. But first, acids are separated into two different categories, binary and tertiary. If you're a binary acid, it is simply hydrogen attached to an element, like HCl, for example. And how we name those binary acids, these are the only acids that should start with hydro. A very common mistake that a lot of kids make is they try to put hydro on the front of every acid name. Not correct. That is only the case if it is a binary acid, aka hydrogen attached to an element. It starts with hydro, you take the root of the element that it is attached to, and you end with ic. Okay? I've heard a mnemonic device for this is my ride has hydraulics. For example, if you were to name this the ionic way, HF would be called hydrogen fluoride. My ride, it ends with IDE, has hydraulics. Hydraulics. If it floats your boat, float it. If it doesn't, then just, memorize it, that sort of thing. The other category is tertiary acids, aka hydrogen attached to a polyatomic ion, or a chemistry gang, as I like to call them. And all you have to know is what the gang ends with. Whatever the suffix of the gang is, that's what's going to determine the suffix of your acid. If the gang that it's attached to, or the polyatomic ion that it's attached to, ends in ate, then the ending of the acid becomes ic. If it ends in ite, then it becomes us. The mnemonic device that I like to use for this is I ate something icky, so I drink Sprite because it is delicious. Looking at our example, we have hydrogen attached to the polyatomic ion sulfate, SO4, with a charge of -2. Therefore, the ending becomes ic, sulfuric. If you said sulfic acid, I don't blame you. For whatever reason, scientists believe that sulfur, when in the presence of acids, should be used in its entirety. Whatever, right? Whatever. So sulfuric acid, if you said sulfic acid, I'm sure your teacher would, be a little lenient with you. And then SO3 with a charge of -2 is sulfite. And so because it ends in ITE, it becomes sulfurous acid. So let's look at a few examples here. We have H3P. This is just hydrogen and an element. Therefore, it is binary. So this one should start with hydro. And P is phosphorus. So this one would be hydrophosphoric acid. HClO3. All I have to do is look at my polyatomic ion chart. I see that ClO3 is chlorate. It ends in ate. Therefore, the ending becomes ic. So it is chloric acid. PO3 with a charge of -3 is phosphite. It ends in ITE, therefore it should become us. So the ending, or the name of this acid is phosphorus acid. Phosphorus is just like sulfur in that for whatever reason, scientists believe phosphorus should be used in its almost entirety when naming acids. Weird. Hydro. This tells you that this is not a polyatomic ion that the acid is comprised of. This is hydrogen attached to an element, and that element must be sulfur. Remember to crisscross your charges when you are writing these compounds, right? We crisscross our charges in order to balance it out. Sulfur has a charge of 2, so the formula for this should be H2S. Bromic acid, if it ends in ic, that tells you that the polyatomic ion that it's attached to ends in ate, so I'm looking for bromate, which is BrO3 with a charge of -1, so the formula should be HBrO3. Hypochlorous acid, that's not hydro, that's hypo, but it ends with us, which tells you that the ending of the polyatomic ion that's attached to is ite, therefore I'm looking for hypochlorite, which is a formula of ClO with a charge of -1, therefore the formula is HClO. Just a little review on naming acids. Practice all you need to. Now, let's discuss strong acids versus weak acids. A strong acid will dissociate completely, and we're going to talk about that a little bit in a second, but you need to know what the 7 strong acids are. And I have a little mnemonic device for this as well. No so clocloclebri. No, so chloride, right? You can see it very, very nicely written out for you right here. But what that stands for is those are the elements aside from the hydrogen, because hydrogen's in every acid. No, so chloride. The NO in nitrate, the SO in sulfate, the ClO in chlorate, so on and so forth, right? But you have to know how many hydrogens are attached to it. But this is the list of the 7 strong acids. It doesn't mean that an acid outside of this list of 7 won't melt your face off. It absolutely will. It's just that these guys behave a little differently when in solution than all of the other acids. Very, very, very important to know. So what is dissociation? Well, what it means is that when you put it in water, it's going to separate into its pieces. Okay? For example, NaCl is comprised of one Na and one Cl. Well, when you put it in water, they sort of break up the band. They realize, sodium's already given the electron, chlorine's already received it. We've done everything we need to do here, right? So you're good to go, I'm good to go, let's go our separate ways. So sodium is going to go off, but now that he's lost an electron is now Na+, and Cl, now that he's gained an electron, is Cl-. Okay? So they go off in their own directions. Well, the same thing goes for the strong acids and the strong bases. Strong acids and strong bases dissociate completely, meaning that every single molecule that you put into water will break up into its pieces. HCl is one of my 7 strong acids. So every molecule of HCl is going to split up into H plus and Cl minus, and they're going to go off in their separate directions. Calcium hydroxide is a strong base. We'll talk about those here in a little bit. But notice that calcium hydroxide, this little subscript is going to throw a little curveball into this. There's one calcium, and calcium has a charge of 2, and there are 2 hydroxides. Hydroxide is a polyatomic ion, OH. It's O's, never H's in chemistry. There are no H's in chemistry. And so hydroxide, there's 2 of them. They're going to split apart from the calcium hydroxide. So this is going to split apart into 1 calcium, 2 plus, and 2 OHs, 1 minus. Okay? So 2 hydroxide ions and 1 calcium ion is what they're going to break up into. If you have an acid or a base that is not in that list of strong acids, strong bases, then they only dissociate partially, usually about 5%. And it's the reason, this is the reason that strong acids and strong bases and ionic compounds are strong electrolytes. Because they all become those ions are able to conduct electricity. Weak acids and weak bases are only weak electrolytes because only some of them become ions. And because there's not as many ions there, they don't conduct electricity as well. So almost always when the acids are written in solution, they show them as hydrogen ions, like in this first example right here, HCl becoming H plus Cl minus. However, if you're looking around online, you could see it written the second way as well. Now, I understand that this equation does not add up, but let me tell you what's going on here. The solutions that we are discussing are in water. So what's occurring is this hydrogen ion is essentially attaching to a water molecule, which then therefore becomes a hydronium ion. Hydronium is H3O with a positive charge. Okay? And it's one of the things that makes a solution actually acidic, is the ability to attach that water molecule or produce these hydrogen ions in solution. Speaking of which, let's discuss the definitions of these acids and these bases that we're talking about. They're going to use 3 different names here, and they each have a very specific twist on what an acid is, what a base is. Kind of nitpicky. This is my least favorite part to talk about because it really is just, you got to memorize it, sadly. But in Arrhenius acid, one of the preliminary definitions of what an acid was any compound, any substance that gives up hydrogen ions or produces these hydrogen ions in water and therefore can form hydronium ions in water. But then 2 scientists by the name of Bronsted and Lowry revised it, and they said, well, is that always the case? Is that a 100% thorough definition of what an acid actually is? You know what? I think an acid should be defined on some other attribute of them, and I think it should be the attribute that they donate a proton. Because what is a hydrogen plus ion? Well, hydrogen only has 1 proton and 1 electron typically. And if you take away that electron, well, then all that's left is a proton. So essentially, an acid is anything that's going to donate a proton. And then another scientist got his own definition for it, and he said, no, 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 I don't think it should be based on the hydrogen ions. I don't think it should be based on the protons. I think a Lewis acid is anything that is going to accept a pair of electrons. And so you see that they each have their own very specific definition on it. And then acids are also referred to as to how many protons they're able to give up. Monoprotic versus diprotic versus triprotic. That is simply how many hydrogens they have, essentially. HCl has one that it can give. H2S has two. H3P that it can give as well. The more an acid dissociates, right, the greater percentage of molecules that break up into their ionic pieces, that is what determines whether or not an acid is strong. Remember that a strong acid dissociates 100%. A weak acid typically only dissociates about 5% or so. So what is a conjugate base? What is a conjugate acid? Well, if an acid is something that is typically willing to give up a proton, let's just stick to the more simple definitions. Let's stick to the Arrhenius acid or the Bronsted-Lowry definition. Okay? Anything that is going to detach a hydrogen or give up a proton to the water. Well, if that's what makes you an acid, if the ability to give up a hydrogen is what makes you an acid, as soon as you don't have that ability anymore, well, then you're not an acid. And so the conjugate base is what the acid becomes after it gives up that hydrogen. Conversely, the base, which we'll discuss their definitions here in a second, the conjugate acid is what the base becomes after it accepts the proton, seeing as the base is the opposite of the acid. So let's look at a couple examples here. Okay? Let's look at the cause and effect, the before and the after. See, we've got these semi-complicated compound right here and water. And then we've got a change over here. Well, what took place? Let's look at the more simple compound first, water. Water is H2O, but on the other side, it lost a hydrogen. So what did water behave as in this circumstance? Well, because he gave up a hydrogen, he is the acid. And what does the acid become? It becomes the conjugate base. It lost the thing that makes it an acid, the ability to give up a hydrogen. Therefore, it became basic, essentially. And notice that a base is the exact opposite of an acid. It's the thing that is going to accept the proton. Well, who gained that hydrogen? It's this compound right here, C6H5NH2. It added one on the other end along with that positive charge. It gained the H+. The base becomes the conjugate acid. So notice that the water is behaving as an acid in this example, but behaving as a base in this example. So let's zoom in a little bit closer. H2O becomes H3O+ in the product side of this reaction. So it definitely didn't lose a hydrogen. It gained an H+. And who gave it to him? HNO3, which if you're using the naming rules, that's nitric acid, one of our 7 strong acids. So if you can name it and it has acid and it's a name, pretty safe bet that that's the acid in an equation. But there are some substances that can go both ways. Water is one of the prime examples. And we'll talk about that definition here in a little bit as well. But it can act as both an acid and a base. But notice that the acid always becomes the conjugate base, and the base always becomes the conjugate acid. To put this plainly, there are such things known as conjugate acid-base pairs. And what that means is that is talking about a before and an after, a cause and effect, essentially. So water is a base, and then it becomes a conjugate acid. These two are pairs. And then HNO3 becomes NO3-. These two are pairs. There's different ways that they can word that, but they all mean the same thing. It's a before and an after, a cause and an effect, essentially. Okay, so now we've talked a whole lot about acids. Let's talk about what bases do. Bases aren't as prevalent in our diets, but if you ever said a bad word when you were little and you got soap in your mouth, that's what my mom did when I was little. Very, very bitter. You want to wipe your tongue off, it's not pleasant whatsoever. But there's not too many bases whenever we're actually, eating normal food, that sort of thing. However, bases are in all of your cleaning products. And if you have soap in your hands, right, it feels super slippery, right? And you've seen all the cartoons where they slip on a bar of soap on the ground, that sort of thing. They have the opposite effect on litmus paper. Acids turn it red, bases turn it blue. And they have a pH that is higher than 7. And where acids kept phenolphthalein clear, bases actually turn it pink. So you can see that when it's neutral, phenolphthalein still remains clear, but when in a basic solution, even if it went, it didn't have to go all the way to 10, maybe it went to 8, it would turn slightly pink as well, that sort of thing. So now, bases are very, very easy to name, though, because they are almost always a metal attached to a hydroxide. And so that's just an ionic compound. All we have to say is the metal name and then hydroxide. Not so bad, right? I don't have to worry about eights, the icks, the ites, the us's, the hydros. Nothing to worry about there. There are examples of bases outside of these. However, the most common one is NH3, which is also known as ammonia, and it is a weak base. Your strong bases are your first and second groups on the periodic table when they're attached to hydroxides, except for magnesium and beryllium. Those are your strong bases. Okay, so there should be 7 strong acids and 8 strong bases that you're looking at. And there's some debate for some of those within those lists, and some just outside those lists, but that's the comprehensive list that we're going to utilize here. Well, just as there were different definitions for acids, there are different definitions for bases. They're the exact opposites from one another, though. So whereas an Arrhenius acid donated hydrogens to water, an Arrhenius base donates hydroxide ions in water. Why? Because all of our examples we saw here have hydroxides, except for NH3, which is what brought up the need for a secondary definition. Because not every base or every substance that acts as a base actually has a hydroxide to work with, we had to revise it. And so Bronze and Lowry said an acid is something that gives protons, while a base is something that is going to receive those protons. And whereas a Lewis acid accepts a pair of electrons, a Lewis base is the thing that gives them up and donates them. Very important to know, an acid and a base, both threatening on their own. I know in the movies it's always the hero being dangled over a vat of spooky green acid, but it could be just as terrifying to dangle them over a vat of spooky base. It doesn't have the same ring to it, right? I'm going to dangle you over a vat of calcium hydroxide. It just doesn't sound the same as hydrochloric acid. And yet, it could have the same effect on your body. They're very, very, very aggressively reactive to, compounds in your body. However, it's just not the same ring to it, not the same exposure. However, if you spill them in the lab, they're both equally dangerous. But what you do is you pour the opposite of it on top of it. If you spill an acid, you pour a base on it. If you spill a base, you pour an acid on it. And the reason why is because that is going to trigger a neutralization reaction. They are both threatening on their own, but when they come together, they're essentially harmless. Okay? Now, that doesn't mean that if you just pour any amount of acid and any amount of base, that you can just take a scoop of it and lick it up. No, you got to be very accurate with it. However, if you are accurate with it, it's pretty much harmless. And it always, always, always produces a salt and water. Now, that does not mean the salt that you sprinkle on your French fries. A salt is essentially any positive ion with any negative ion. So essentially any ionic compound that you're familiar with. But H2O is formed in every single one of these reactions. And so when we look at this example down here, HCl, hydrochloric acid, and sodium hydroxide, both of these, this is a strong acid, this is a strong base. If I spilled one of them on the floor, I'm not going to just immediately take a paper towel to it, because that can easily burn through the paper towel and then burn my hands. I'm not about that life. But if I pour the same amount of the opposite on top of it, I really do just get salt water. And if you were accurate and you trusted your measurements, you could literally lick it off the ground and be totally fine. Not that I recommend that. Not that I can guarantee that you are a perfect scientist, as no one is. But you really could. Kind of gross, but awesome. Neutralization reactions always form a salt and water. And so now let's talk about that definition we mentioned earlier. Amphoteric is the term for a substance that can act as both an acid or a base. Something that can give a proton and something that can receive a proton. The telltale sign is they've got to have a hydrogen out front and they've got to have a negative charge out back. However, the most common example of an amphoteric substance is water. If it loses one, it becomes hydroxide. If it gains one, it becomes H3O+, hydronium. Both are very, very common substances. But look at HCO3- bicarbonate. It's got that hydrogen out front, so it has something to give. And it has a negative charge out back, which means it is willing to accept a positive charge. Now let's begin to discuss the mathematical calculations associated with acids and bases. So what they've done is they boiled it down to what is called the pH scale, which is a simplistic way of looking at how strong of an acid something is or how strong of a base something is. Well, really, what makes something a really, really strong acid or a really low pH is having a lot of H pluses in there. As we've discussed previously, acids donate H pluses to the water. Well, what makes something a really, really strong basic solution is having a bunch of hydroxides in the water or a high concentration of OH minuses in that water. So look at these formulas that we've got right here. First of all, if I see a P in front of something, if I see a P, which we see several times, pH versus POH, that simply means that they have utilized what is called a logarithmic function in their calculator. What they did is they took the negative log of whatever the concentration of hydrogen ions in solution was, and they plug it into their calculator. What the heck is a log, you might ask? I've never seen that before. I haven't taken Algebra 2. Well, by golly, you're in for a treat. Calculators on my left, on my right, they're everywhere. Oh my goodness. Well, if you're using the calculator on the left, the more simplistic kind, notice towards the top left corner, below that second button, you'll see the log button. There it is right there, okay? We're not going to go into what a logarithmic function actually is, but what it does is it breaks down things into scales of 10, essentially. And so what that means is if something has a pH of 2, it is 10 times more acidic than something with a pH of 3. And a pH of 2 is 100 times more acidic than a pH of 4. See, 2 steps away, it's 10 times 10, that sort of thing. And then, if you're using the more complicated graphing calculator like you see on the right-hand side of your screen, the log is right next to the number 7, okay? That's all you're really going to need to use there. We'll go into different mathematical calculations here as well. But we want to look at a few constants here, okay? This is one that you don't necessarily have to use, but it's very important to understand, okay? And that is the concentration of H plus hydrogen ions and the concentration of OH minus or hydroxide ions will always multiply together to give you this number, 1 times 10 to the negative 14th. There is no solution where that is not the case, okay? And then you also, this is the more simple constant to remember and the one that I'm going to utilize in my calculations here momentarily, pH plus POH of a solution will always equal 14, okay? So let's keep those constants in mind. You definitely want to keep these equations off to the side for yourself until you get used to understanding what they're actually doing. If I'm solving for the pH, notice that it's just H, I'm going to use the negative log of the concentration of H pluses. If I'm going to solve for the POH, then I'm going to use the negative log of the hydroxide concentration, OH, right? So you have to really pay attention to what you're solving for and what you're utilizing. Keep in mind, we're on that pH scale between 0 and 14. There is such a thing as a POH scale, and is the exact mirror image of the pH scale. But pH is what everyone uses. So if we are below 7, we are an acid. If we are above 7, we are a base. And if we're right on that 7 mark, we are neutral. And you can look at this little scale. This is one that's just pulled offline. Lots of cleaning products in the top end, the higher end of the pH scale. And lots of food items that you're going to see on the lower end. And so we actually do consume a lot of acids. And the reason why our body is built to withstand is because of different buffer systems within our body. But also on top of that, the stomach acids within our stomach cavity are acidic. Stomach acids, right? And so they're built to handle it. So let's look at a few examples here. What is the pH of a 0.0001 molar solution of HCl? The biggest thing to realize, and because we're just in sophomore to junior, pre-AP, on-level chemistry, that sort of thing, all of our calculations that we're going to be utilizing are implementing strong acids. And the reason why that's important is because what do strong acids do? They dissociate completely. If we were doing weak acids with this, the math completely changes, and that's more of an AP chemistry concept. But what this means is that if I have a 0.0001 molar solution of HCl, I also have a 0.0001 molar concentration of H+, because what does every molecule of HCl do when they get put into water? It separates into H+ and Cl-. And so the concentration of this acid is the same as the concentration of the H+. Therefore, it is a simple calculation. Let's look to the board to solve it. So now we're going into our pH and POH calculations, starting off with calculating the pH from hydrogen or hydroxide ion concentration.
Starting with example number 6 in your notes, what is the pH of a 0.0001 molar solution of HCl? The important thing to remember here is that HCl being a strong acid means that every single molecule of HCl, when it's put into water, is going to split up into two pieces. It's going to dissociate. It's going to break up into its different components. It's going to break up into hydrogen ions and chloride ions. So if they're giving you the concentration of HCl, then they're also giving you the concentration of H+, because every single molecule is going to do this, and there's only one H for every HCl. Therefore, it's a 1-to-1 ratio. So when they tell you, what is the pH of a 0.0001 molar solution of HCl, that is also telling you the concentration of hydrogen ions, 0.0001 molar. And so then, it's as simple as just looking at our formula. To calculate the pH, it's equal to the negative log of H+. And so all I got to do is negative log of 0.0001 is going to give me my pH. And then something we're going to note here is that pH is a little odd with its sig figs. So when we plug this in, we're just going to get 4 in our calculator. This measured value that they gave us has 1 sig fig, but all the numbers to the left of the decimal in pH aren't actually significant. And the reason why is because when we plug this into a logarithmic function, everything has a base of 10. Meaning that if I have a pH of 4 and something with a value of a pH of 5, they're actually separated by a factor of 10. So these differences get very, very large very, very fast. And so the significant figures are not counted until after the decimal. So technically the answer we want to write here is 4.0 as our pH.
So whereas number 6 kind of disguised what our hydrogen ion concentration was, number 7 is just coming out and telling us. What is the pH of a solution that has a hydrogen ion concentration of 3.4 times 10 to the negative 5th? This one is as simple and as cut and dry as it can get. They're straight up telling you what the H+ concentration is. All you have to do is negative log and then that value. So we'll look to that board here in a second. But let's discuss example 8 here really fast. What is the pH of a 0.00001 molar sample of NaOH? Look at the substance that you're dealing with. It is no longer an acid. They are not giving you the concentration of your H+, because in order to solve for pH, I need the negative log of H+. However, this substance that I'm looking at currently is a base. Therefore, the concentration that they are giving me is not the concentration of H+, it's actually the concentration of OH-, because NaOH does not separate into H+. It just doesn't. The piece isn't there. It separates into Na+ and OH-. Well, what can we solve utilizing the concentration of OH-? What can we solve for? Let's look back at our equations. If I have the concentration of OH-, I can solve for the POH. And then I can utilize the relationship between pH and POH to solve for pH. So this one is a two-step process. You have to pay attention to the substance that you are beginning with. So let's look at those on the board now.
Example 7 reads, what is the pH of a solution that has a hydrogen ion concentration of 3.4 times 10 to the negative 5th? This one's even easier than the last one. They're straight up telling you that the hydrogen ion concentration, H+, is 3.4 times 10 to the negative 5th. So what am I going to use to get to the pH? I'm going to use the equation that solves for pH. pH is equal to the negative log of H+. So all I got to do is negative log this number. Negative log, like so. And let's see what we get. Keep in mind, this number has 2 significant figures to its measurement, so we're actually going to go 2 after the decimal for our pH calculation for sig figs. And so we get an answer of 4.47. Example 8 is a little trickier, and the reason why is because they're not starting you with an acid this time. They're not giving you the hydrogen ion concentration. What is the pH of a 0.00001 molar, 4 zeros, of NaOH? So they're giving you NaOH, and sodium hydroxide is a strong base. However, it doesn't produce hydrogen ions, which is why the concentration of the base is sort of misleading for this. You're going to have to take an extra step. So when sodium hydroxide is put into water, it splits up into Na plus and hydroxide minus. No hydrogen ions to be found, which means the concentration that they give me is not the hydrogen ion concentration, it's actually the hydroxide ion concentration. So that's 4 zeros, 0.00001 molar concentration of hydroxide, and I can't use the hydroxide ion concentration to solve for pH. pH only utilizes hydrogen. So what I'm going to have to do is I'm going to use the hydroxide ion concentration to solve for pOH, and then I'm going to use this third equation, this constant that we have, which relies on the fact that pOH plus pH will always equal 14. So let's go ahead and plug in negative log of 0.00001, right? And when you get a little bit of practice with these, you start to see patterns, or if you have experience with logs, then you can actually do this sort of in your head, looking at the number of zeros. So your pOH is 5, and I guarantee if this were a multiple choice quiz or test that you're taking, that's one of the answer choices. And it's going to really stick out and look really juicy to you, but you have to pay attention to the fact that you started with a base and not with an acid, because there is one extra step you got to do. pOH is 5, which means if I subtract that from 14, because pH plus 5 is equal to 14, then I can very readily solve for the pH. And so the pH is actually going to be 9. And let's go ahead and give it that sig fig after the decimal, and we're good to go.
So now, what if we want to go backwards? What if they give us the pH or the pOH of a solution, and we need to find the concentrations of the H plus or the hydroxide ions? Well, there is a way to do it in our calculator. So let's look back at our equations. Let's look back at our calculators here in just a moment. It says that to solve for the concentration of H plus, I need the antilog of the negative pH. Pay attention to those negatives. You have to put those in there. If you don't, you're going to get it wrong. And to solve for the OH minus, the concentration of hydroxide, I need the antilog of the negative pOH. You're looking at your calculators. Oh my gosh, there's no antilog button. But all you have to do is hit the second button, which is found in the top left of either calculator, whatever you're using, and then hit the log button. And what it's going to look like is it's going to look like 10 to the, okay? And what that is the anti-log function in your calculator. But please, please, please do not forget that negative in front of your pH or that pOH. It's not going to work if you don't put it there. Example 9. What is the hydrogen plus concentration of a solution that has a pH of 4? They're straight up giving you the pH, and look at what you need in order to solve for H plus. You need the pH. So this one is cut and dry. Second log, negative 4, and I'm going to get my answer. Okay? Let's discuss sig figs of pH. We should have discussed this prior, but let's discuss sig figs. This is a very weird concept. The pH scale is between 0 and 14. And actually, that number, whatever it is between 0 and 14, whatever's left of the decimal is not considered significant. Very strange, right? In fact, the first significant figure is always the first decimal place. So when I look at this pH of 4.0, this actually only has one sig fig. Very odd. Very odd. And so what I'm going to do whenever I solve for this is I'm going to round it to one sig fig. So we're going to solve example 9 on the board here. Let's discuss example 10 while we're here as well. What is the hydroxide concentration of a solution that has a pH of 2.9? Well, look at your equation. What do you need in order to solve for your hydroxide concentration? It's not pH. It's pOH. But what did the problem give me? It gave me pH. So I first need to convert pH to pOH, and then I can solve it. So we have to once again utilize that constant. pH plus pOH is going to equal 14. Solving on the board now.
So now we're going the opposite direction. They're starting us off with pH, and we want to find out how many hydrogen or hydroxide ions are in solution. Well, it's just a flipping of the buttons on your calculator. We use the log to find the pH, and we're going to undo the log to find the H plus or the OH minus. And so what that is going to look like in your calculator is anti-log. And the way that you do that is you hit the second button in the top left and then log, and it will do the inverse of a logarithmic function. But do note, it's the antilog of the negative pH, and it's the antilog of the negative pOH. If you don't have this negative, you will not get the correct answer. Example 9 reads, what is the hydrogen ion concentration of a solution that has a pH of 4.0? Which means all we're going to do in our calculator H plus is equal to the antilog of -4, like so. If I don't have that negative, it doesn't work. And so, my answer that I get, and because our pH was 4.0, it only has one sig fig, one number after the decimal, so will our concentration. H plus is equal to 0.0001. In our last pH/pOH calculation of the day, example 10, what is the hydroxide ion concentration of a solution that has a pH of 2.9? Take a look at all the equations that you can use, and there is the ionization constant of water that you can utilize as well. I like to stick to these because pH plus pOH equals 14 is a whole lot easier than H plus times OH minus equals 1 times 10 to the negative 14. It's just easier. And so, there is no combination of the equations, or there is no one equation that will just go from pH to OH minus. If you look at all of them, there's none. You have to do this in 2 steps. And the way that we're going to do it is we are going to go from pH to pOH, first and foremost, utilizing this constant right here in the middle, pH plus pOH equals 14, and then we can solve for the hydroxide ion concentration using the antilog of the negative pOH. So if they're telling us that the pH is 2.9, 2.9 plus pOH is absolutely going to equal 14. That is a constant, like so. And so, our pOH must be equal to 11.1 then. And now, if we do second log in our calculator, second log negative 11.1, we will get our hydroxide ion concentration. And keep in mind, we have one sig fig still, so our answer is going to have one sig fig as well. Like so. Make sure to mind that negative 11.1. And so we're going to go ahead and round this simply to 8. And this is going to be 8 times 10 to the negative 12.
This is a very, very brief concept before we get into the final concept of the day, which is net ionic equations. Comparing acids and bases through what are known as Ka values. This is more explored in AP chemistry, but briefly appears in our curriculum here. The larger the Ka, the stronger the acid. Okay, so typically how you're going to see this is you're going to get Ka values. The larger it is, the stronger your acid is. So looking at this chart, who is the strongest acid? It's whoever has this largest Ka value here. And this table has done all the work for you. It's actually ordered it from highest to weakest, or strongest to weakest. And so hydroiodic acid with its Ka of 3.16 times 10 to the 9th is almost definitely, and when I say almost definitely, it is absolutely higher than 1.75 times 10 to the negative, which tells us that HI, hydroiodic acid, is certainly a stronger acid than acetic acid, which means it is going to dissociate much more readily than acetic acid. But we already knew that, because we know our list of 7 strong acids, nosoclococlebri. And look at the first 4. The first 4 acids on this list are in the nosoclococlebri list. Nitric acid is actually below the hydronium ion. And remember that hydronium ion is typically formed from these hydrogen ions falling off of the acids and attaching to water molecules. So pretty cool to see there. So let's look at our final concept today, which is net ionic equations. Just a little brief review. We've seen it before. We're going to do it again. Essentially what's happening is these are typically double replacement reactions, and what they are going to do is they are going to either produce A, a precipitate, B, a gas, or C, water. If it doesn't accomplish one of those 3 things, it's a no reaction. But in the end, we want to only take a look at what has actually chemically changed, because there are what are known as spectator ions involved here. And spectators, just like their name, are just watching. They're not really doing anything. And so what we're going to do is we're going to eliminate those that are just watching. So what you're going to need for this are your solubility rules, if you still have those on hand, or feel free to look them up online. But we need to utilize our predicting products tricks that we learned from whenever we were doing double replacement reactions, and our solubility rule. So looking at our first reaction, copper 2 chloride plus sodium hydroxide forms. We have to predict that first, and then we're going to boil it down to the net ionic equation. So we're going to solve that on the board for you. And our last topic of the video of today is a quick review on net ionic equations.
Because neutralization reactions have a very, very unique net ionic equation in that any neutralization reaction results in the same net ionic equation. Very, very cool because it's always going to make water. However, net ionic equations go beyond neutralization reactions, and so let's start with this reaction right here. Copper 2 chloride plus sodium hydroxide. Remember that the point of a double replacement reaction is to produce either a solid, a liquid, or a gas, okay? And that solid that we're looking for is in the form of a precipitate, aka something that does not dissolve in water. Therefore, if you don't have your solubility rules memorized, you're going to need those on hand. If you don't remember double replacement reactions, I like to think of it as the two metals switching places, or I've had a student sort of tackling it like the FOIL method in algebra, which I don't even think they use anymore, but they look at it as the outside guys getting together and the inside guys getting together, sort of a double smile action on the bottom. And so that is going to be our supposed products for this reaction. And so sodium is going to get with chlorine. Do remember to crisscross your charges so that you're balancing your formulas. Sodium is going to get with chlorine though. And copper 2, with a charge of 2, is going to get with hydroxide. So we get CuOH2. Okay? So now we need to deduce whether or not we actually accomplish our goal. Did we make a solid? Did we make a liquid? Did we make a gas? Well, it's very hard to turn metals into gases, so we didn't make a gas. We didn't make water, so we didn't make a liquid, so our only hope is whether or not we made a precipitate. So you're looking at your solubility rules. You know that salt dissolves in water, and wouldn't you know, copper 2 hydroxide is not soluble in water. Therefore, it is our precipitate. So here's a little shortcut with your net ionic equations. Whatever your solid product is, that is the product of your net ionic equation. So we're just going to bring this all the way down. And yes, there's a longer process to this. This is just our review, so we're just, showing you the shortcut, that sort of deal. So now, if I ended with this, then I obviously had to have started with the components that make him on the reactant side. So how many coppers do I have? Only 1. And what's the charge of copper in this situation? 2. So I've got 1 copper ion. Keep in mind it is called a net ionic equation. Therefore, if there aren't ions, you did something wrong. And how many hydroxides do I need to make this recipe? Well, there's 2 hydroxides, and every hydroxide has a charge of -1. Like so. And there's the net ionic equation.
And our second and final example of the day is between silver nitrate and calcium chloride. We're going to do the exact same thing as we did before, except for now this question is asking, what are my spectator ions? So it's not asking for the net ionic equation technically. It is asking for the spectator ions. Either way, we're solving for it.
Final problem of the day is a reaction between silver nitrate and calcium chloride, and the question is, what are the spectator ions? Well, there's a shortcut to this as well. You can write out the net ionic equation, or we're going to predict our products and utilize a little shortcut from there. We don't even have to write the net ionic equation if spectator ions is your question, but we'll go ahead and do it. So, go ahead and switch your metals just like before. Calcium is going to get with nitrate, silver is going to get with chlorine. Calcium and nitrate get together and they make Ca parentheses NO32. Make sure to flip your charges. And silver is going to get with chlorine. They both have charges of 1. And you're using your solubility rules, and you find out that calcium nitrate is absolutely soluble, and silver chloride is insoluble. Well, just as we did before, you could go ahead and take this solid product and put that to your product for the net ionic equation. Or, if the question is simply, what are the spectator ions? Look at who is aqueous in the product side. Because whoever is aqueous in the product side are the spectators. They are the guys that did not chemically change. Therefore, it's going to be our calcium ion and our nitrate ion. Those are the spectator ions. But let's go ahead and answer the full question. Let's go ahead and write the net ionic equation. So this is our product, AgCl. And if we ended with AgCl, well then what are the pieces that we would need in order to make him? Well, I need 1 silver and 1 chlorine for each of these, and we know their charges when they are ions. Silver has a charge of 1, and chlorine has a charge of 1. Like so. And yes, you could balance this equation before. Everything does simplify and reduce at the end, so that's really up to your teacher's discretion. It's always safe to balance the equation if that's what you're answering. Anyways, Unit 9, drawing to a close, and perhaps corona chemistry as well. Quarantine log. Day 99. I've poured much blood, sweat, and tears into this, but I've finally done it. I have found the cure to corona. You see, you start with